In this video, we're going to talk similar trends of electron configurations in the columns. And so we talked about electron configurations that you can kind of look at the block and say, hey, here's the P block, here's the S block, transition metals were our D block. You could know what the last electron to go in is. And each column will end in exactly the same configuration, adjusted simply for the N level. My fluorine ends in 2p5. My chlorine is 3p5. My bromine is 4p5. Each column is lined up with the number of electrons that we expect to see in which orbital. And so that each column will always end in the same S or P and number of electrons in it. You'll just adjust for what N value you're in. This, however, also lets us see a couple interesting things like ion changes. The sodium, potassium, lithium, they all become +1 ions. If we want to think about why, lithium, 1s, 2s, 1, 2, 3. Lithium plus 1s, 2s, 1, 2. When you lose an electron from lithium, you lose them from its highest orbital. Well, the Z effective of the lithium 2s says 3 protons minus 2 core for +1. Your valence are your shell that is the highest that has electrons in it. For neutral lithium, that was the 2 shell, but for lithium plus, for the cation, it's now the 1 shell. There are no electrons in the 2 anymore. So if another electron was to be taken, it would have to take from the 1s. Well, the 1s sees 3 positives and no core for a 3 plus. It is significantly more difficult to remove that electron from lithium plus than it was from lithium. If we think about this for sodium, well, sodium is neon 3s1. Sodium has 11 protons. Neon has, well, there's 10 electrons on it, so 10 core electrons for a +1. Which is what we saw for lithium. That whole column should see a Z effective of +1. But after that, you're down to the 2 S's, the 2 P's, the 1 S. There's still 10 electrons on sodium. So if you go down to sodium plus, which just looks like neon, well, I've lost my N equals 3 electrons. Now the outer edge electrons, the ones at the surface, the ones we would consider valence, are the N equals 2s. The N equals 2s, well, there's still 11 protons, but there's only 2 core electrons. So they see +9. Removing that first electron from sodium is pretty darn easy. Removing the next is significantly harder. As a result, sodium generally just loses 1. It barely held on to its first, but it's really holding on to its second and later. And so our lithium, our potassium, our sodiums, they all tend to get +1 charges. There's a similar effect going on for magnesium and calcium. And so if we think about ion charge, we're going to say, well, there's +1 for lithium, sodium, potassium. There's +2 for beryllium, magnesium, and calcium for the same idea. Once you removed your outer end shell, getting rid of your cores would be very difficult. Magnesium, which will end 1s, 2s, 2p, 3s. Originally it has 2 electrons in the 3s, but once it becomes a 2 plus, it only has electrons in earlier N values. Magnesium is 12 protons. There's 10 core electrons. So initially it's a +2 Z effective. But as soon as we go down to only having 2 core electrons once we've gotten rid of 2 of our charges. Well, that means everything in the n equals 2 sees a 10 plus Z effective. Similarly to the sodium, it's just not going to lose a second electron. They're way too strongly attracted. If we go far over to the carbon, the nitrogen, the oxygen, the fluorine, as we go farther on the right on the periodic table, well, we don't expect these to be cations. They don't tend to lose electrons. Why is that? Well, if we think about the fluorine, let's go to the extreme end of it. Fluorine, 1s, 2s, 2p, 1, 2, 3, 4, 5, 6, 7, 8, 9. Fluorine is the 9th element, so it has 9 protons. And its 2 shell orbitals see only, well, n equals 1, it sees only 2 electrons. So there's 2 core. They are a +7. Those electrons already see a massive positive charge. The 2p and the 2s electrons are not easy to remove from fluorine. They see a massive charge. They really don't want to leave the fluorine. In fact, there's so much attraction that another electron floating through space would rather drop down and attach. Because even if you attach one, well, there's still 9 protons and 2 core electrons for a +7. Adding another electron doesn't change the Z effective. And so in this case, it's really easy to pick up one more electron and fill in my 2p and my 2s. So we can make F-. Why do we only pick up one electron, though? Why not go to F2-? Well, if we did that, we can have our 1s, our 2s, our 2p's, and a 3s, because fluorine 2- is going to have 11 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. To get that second extra electron on the fluorine, it has to go to the 3s. It has to go way up in energy to another shell. And if we think about how strongly that one's held, well, there's 9 protons. Still, it's fluorine, but now there's 10 core electrons. For Z effective of -1. As far as that 3s electron is concerned, it's not actually being attracted, it's being repelled. And so getting a second electron on fluorine, because you have to put it in a higher shell, it's not going to be attracted. This is why we see the same charges on a column. We expect a -1 charge on the fluorine, chlorine, and bromine. We expect a -2 oxygen and sulfur. We expect a -3 on nitrogen and phosphorus. Because that's the most electrons we can get in before any more would have to go to a higher shell. That higher shell isn't going to attract them, and so they stop adding. So we can use Z effective to help us see trends in ion charges in our periodic table, and they're really tied to electron configuration. That first extra electron on fluorine fits in just fine because it is going into the same shell that the other valence electrons are already in. Try to go to a higher shell, and energetically, it's not favorable.